Alright, in this video we're going to go through some examples of limits using multivariable calculus, or those functions that are in 3 dimensions or higher. The first example technically is just in R2, and it's just using a parameterization, which you might come across. So this one shouldn't be too challenging for us to do, just using our previous knowledge. And so we can actually use direct substitution here because it's continuous, and what we end up getting is the point 1 minus 1. Okay, I just wanted to show you that brief example to get you ready for what may be coming up. Okay. Um, this next problem is a little bit more interesting. So we have the limit as we approach the zero vector, or the origin, of x squared minus y squared all over x squared plus y squared. And so kind of our first attack with these things is to keep in mind that intuitive definition, and we want the limits to be the same along all paths. Well, maybe it would be useful to start looking at some paths, right? There's a couple easy tracks to follow, one of which is to start with the axes, right? So let's look along, along the x-axis. Okay, and when we do this, just keep in mind that the points have the form x comma 0. Okay, so, well then, right, then here I get the limit, and I'm just going to use vector x approaches the 0 vector, and so nothing has changed there, but now my function is actually just x squared over x squared, right? Because the y's are 0, and well, that's just 1. Okay, so now that's fine. Let's see what we get along a different perspective. So let's look at another axis. So let's look at along the y-axis. Okay, when I do this, the point should be of the form 0 comma y, and what I get as a result, okay, limit vector x approaches the 0 vector, I think I get minus y squared over y squared, again because now the x's are 0. Okay, and so I end up with minus 1. Okay, well, consequently, because of what we were saying before, these don't match, right? So then I'm going to say the limit here does not exist. Okay? And I can actually see this limit not existing in a different way. So, welcome back to our friend CalcPlot3D, right? And if I plot this function, so you can see off to the left here that I have x squared minus y squared, and I can see that as I approach along the vector, or the x-axis, right? If you're just following my cursor, it is approaching 1, and then suddenly it bloop, and then it drops down and comes back up, right? And then if I just change my perspective a little bit, you can see with along the y-axis, there we go, okay, so there's the y-axis, and I'm down here at minus 1, I go, it's minus 1, and then bloop, and then back down to minus 1. So what I would say from here is that, well, we've talked about this idea of smooth, right? And we don't have the technical tools that use that language formally, but there is some sort of anomaly, or it's a bit of unsmoothness right near the origin, which is going to cause the limit to not exist. All right, let's press on and look at a couple more examples. So now we have a different example of the same flavor, right? We have xy over x squared plus y squared, and when I look at this a little bit in detail, okay, I'm going to begin the analysis in the same way as I did before. I'm going to look along the x-axis. When I do that, I get the limit as x approaches the 0 vector, and then, well, now I just get 0 in the numerator over x squared, which is just 0. Okay. Well, that's fine. Let's see what I get along the y-axis. Okay, again, limit as vector x approaches the 0 vector, and, well, that's also going to be 0 over y squared. So that's nice. So this limit might actually exist. Pressing on, now I'm going to change things up just a little bit, and I'm going to look along a different path, okay? The path that I'm going to choose is along the line y is equal to x. And actually, to be more general, if I look along any line, okay, you could certainly do y is equal to x, okay? What do we get if we go along this path? Limit as x approaches the vector 0, and I believe I get mx squared, right, because y would be that mx, and then I get down here x squared plus m squared x squared, which I can simplify, right, by dividing by an x squared to everything. Let's see, limit vector x approaches vector 0. Okay, and I get m over, oops, like that, m plus 1 over m squared. Well, if m is 0, this is fine, right? But then I just get along the x-axis. But what I see now is that, well, this line and, well, any one of those along the axis, not the same. So this means that the limit, oh, that's terrible handwriting. Limit, wow. Limit does not exist. Okay? And again, I could check this just as I did with the previous one. I do have this made in CalcPlot 3D, and so you can kind of see it. It's tough from this perspective. I'll change perspectives in a minute, but you can see that as you turn, there's a bit of an anomaly right at the 0 vector. Okay, because you can see, okay, well, it's mainly, if you look at along the x-axis, yes, it is 0. It is sort of turning, and then along the y-axis, yep, it's 0, but it's kind of sloped up. And then along the line y is equal to mx, it's a different height. Okay, so that's another example of a limit that does not exist. And we have one more example. Okay, and it's the example x squared plus, or x squared y over x to the 4 plus y squared. Now, you're probably thinking that this limit is going to exist, and I'm going to tell you, well, maybe. Let's see. I'm going to begin with my standard approach. Okay, so x-axis, I get the limit, x approaches the 0 vector of, well, surprise, 0 over x to the 4th, which is 0, okay, and then we do along the y-axis, limit vector x approaches 0 vector of 0 over y squared, still 0, okay, well, this is good so far, and we're going to try the line y is equal to mx, okay. Let's get that going here. And what do I get with this? Well, I get m x cubed over x to the 4th plus m squared x squared. Okay, I could divide by x to the 2nd out of everything, but eventually what you end up getting is 0, right? I'll let you confirm that. So this is fine. So at this point, you're like, oh, great, we've shown the limit is 0. Well, let's look at just one more path. I'm going to look along the parabola this time. Y is equal to x squared. Why did I choose this path? Well, because it's magic and it works. But there is no magic in math. There's a reason. Limit as x approaches the 0 vector. And then you get x to the 4th over x to the 4th plus x to the 4th. Oh, that's just 1/2. Guess what? The limit does not exist. Okay. Now, you're probably wondering, how in the world do you know which paths to pick? Well, generally, I'm going to tell you, picking these 3 standard ones are really good ideas. X-axis, y-axis, and look along the set of all lines. Okay. Generally, those are going to tell you whether or not the limit exists or does not exist. Well, or sorry, does not exist. For other things, what I would suggest is kind of look at the powers occurring in your function that you're given. Okay, maybe there's some relationship here. I noticed that for this particular path, the reason I chose it was because, well, I noticed that y has a power of 1 and x has a power of 2, and there's that sort of relationship down here too. So maybe if I look along that path, maybe that'll give me something that's more interesting. Okay, so that's just a general strategy that I try to do, is look at relationship among the quantities that I have in the problem. Otherwise, you could always try to type this into Wolfram Alpha. I'm going to tell you it's very challenging to do this in Wolfram Alpha Pro, but if you could check your answer that way as well. Okay. Otherwise, we did some things in CalcPlot 3D, and you can visualize the surface there. And if you notice any areas of unsmoothness or areas where there's different valleys or gaps in there, that's probably going to mean that the limit doesn't exist. Okay? To prove that it does exist, well, that could be a little bit trickier of a situation. You could try direct substitution, but again, if you do direct substitution here, it's not going to work. Okay? So be careful with that. But that's kind of the end of this video. In the next video, we'll have some more tools to use to find limits.